One end of a long rod is leaning against a vertical wall, and its lower end is on a horizontal surface on the floor. The lower end is being dragged away from the wall with a steady speed v. Your interest is to find the velocity of the upper end of the rod at the moment when the rod makes an angle theta with the horizontal. So as the end A on the floor keeps moving with a steady speed v, well, how does the velocity, say capital V of the upper end, change? And that you want to find when the rod is leaning at an angle theta. Well, velocities are rate of change of positions. So if you can find a position relation between positions, you should be able to find a relation between velocities. You could do that by, say, this could be the origin. This, let's say the coordinate of this is, say, x0, and the coordinate of this is, say, 0, y. So the length of the rod L, say L, is root x squared plus y squared. This does not change. X and y are variables here, and rate of change of x is given to us, that's small v, and you want to find rate of change of y. And this is the relation x and y. The length of the rod does not change during the motion, right? So this is to be differentiated so that dl by dt would be 0. We could do that. Dl by dt equals half x squared plus y squared power minus half. To differentiate that, 2x, we're differentiating this with respect to time, right? So 2x dx by dt, dx by dt is small v, dx by dt plus 2y dy by dt, right? And this should be 0. So this will be 0. So you would get 2x dx by dt plus 2y dy by dt equals 0. And you want dy by dt. dy by dt is equal to minus x by y dx by dt. So this is capital V, minus x by v. Now that would be cot theta, right? Cot theta would be x by y. So this is cot theta, and this is capital small v. The minus n is to indicate that y is decreasing as x increases. So that's the relation. You related positions, because the rate of change of position is velocity. So if I find a relation between velocities, I can find a relation between, if I find a relation in positions, I can find a relation in velocities. Done. This is one way of doing it, a fairly straightforward way of dealing with it. We can also handle this differently. Well, during the motion, the length of the rod does not change. So we can directly relate to that length L and say the end of lower end of the rod has a velocity v at an angle to the rod, and the velocity component along the rod is v cos theta. So a velocity of A along the length of the rod, and this angle is 90 minus theta. So the component of velocity of the upper end, say call it B, along the rod we want. This is small v cos, that will be v sin theta, right? This angle would be theta, right? So this angle would be theta, v sin theta would be the component along the rod. So v cos theta, that is the rate at which A is moving away from B, and this is the rate at which B is moving towards A, and this must be 0 because the rod's length does not change. Components of velocity A and B along the length of the rod must be same. This must be 0. So So capital V is equal to V cos theta by sin theta, that is V cot theta. Well, one step answer here, right? So this is well, minus sign we put because L decreases as well, B, say, imagine B moving towards A. For a moment forget that B is moving down the wall. If V component along the rod, if B moved that way, length of rod would decrease, and this would cause increase in length of the rod, but length of the rod is not changing, right? So this is it. This is an interesting way of doing the calculation. There is another very interesting way of solving this. This rod is in combined translation plus rotation. If the rod was moving like this, making the same angle with the horizontal, then that's pure translation. If the end A were fixed and it rotated like this, that would be pure rotation. But now the orientation of the rod is changing plus the rod is translating. So you have well, combined translation plus rotation. In combined translation plus rotation, it's possible to find something called instantaneous axis of rotation. Now that can be found by doing something like this. This is the instantaneous axis of rotation. How to get this? In rotation, velocities must be perpendicular to the line joining the particle to the center. So if I draw a perpendicular to this V, it must lead to the center. If I draw a perpendicular to this V, it should lead to the center. So this must be the center, instantaneous axis. This is instantaneous axis. It's combined translation plus rotation, and that's instantaneous axis. So the angular velocity about I, this will be V by this length. Then that length will be L sin theta. This is L sin theta and this is L cos theta. So angular velocity omega of the rod at this position is V by L cos theta, right? This V by L sin theta, L sin theta. And this should also be same as capital V by, that's L cos theta, right? This is the, for this V by this distance, that is L cos theta. So capital V is L goes away, V cot theta. This is another very interesting way of solving the problem. Well, you're branding the motion. It is combined translation plus rotation. And we have some ideas about combined translation plus rotation. We can find what to call an instantaneous axis. And once you know the instantaneous axis, you can define the velocities of any point on the rod. And how to define the instantaneous axis? You realize that velocities of the moving body must be perpendicular to the line joining their positions to the center. So we are finding that center there. Also, if I ask which point on the rod has the velocity parallel to the length of the rod, you should be able to easily find it. Drop a perpendicular here, because the velocities of the points must be perpendicular to this line. This will be the velocity of that point, so along the rod. So if you are asked where is that point, you can find it, right? So it's good to see it this way too. And what kind of motion is this? It's combined translation plus rotation. It is only translation. All particles of the body would have same velocities. And if it's just rotation about an axis, stationary axis, that also would be simple. V's will be R omegas. But this is combined translation plus rotation, and we have to find that instantaneous axis. So done.